So we've learned the principles underneath the theory of special relativity, and we've learned that we live in Minkowski spacetime rather than Euclidean space with a universal time dimension tacked on. And this has had fairly profound effects on our ideas of what space and time are and how they work. It's also affected our other physical theories. So we've looked a little bit at how it changes some of classical mechanics, particularly when we start talking about energy momentum in terms of four vectors. We discovered some deeper truths about the nature of energy from that. And we've also gone to some effort to introduce tensors in a more general formalism so that we can bring on electromagnetism onto that footing. Now, what have we gained from all this? Well, first of all, special relativity is the correct theory, right? It's the correct theory of what we see around us. In particular, you can measure time dilation by jumping on a plane. So they've done that. They did that over 30 years ago. A couple of atomic clocks next to each other, reading the same numbers. One goes on a plane, flies around the Earth, comes back. It's reading different numbers now. Okay, so we can measure it. But it's not just for small effects. Although sometimes time dilation can be dramatic, the only reason we know about a large number of the fundamental particles around, a large number of the particles that we detect, is that they typically are generated moving very close to the speed of light, in which case they're incredibly short half-lives. Normally they disappear in femtoseconds or crazily short amounts of time. Because of time dilation, they last long enough for us to detect them. None of our timing in satellites would work without some kind of relativistic correction. In fact, we have both special relativistic and general relativistic corrections in the timing in satellites. Relativity is absolutely critical to describe most of what we see in astronomy, both in an observational sense and also in terms of explaining what we see. It also fixes electromagnetism in different frame. Remember the thought experiment we had where we had the electrons in the rest frame and the electrons in the moving frame, and how that seemed to do different things. Well, when you have all the apparatus of relativity together, electromagnetism behaves very naturally. Another good example of that is just the force on a charge due to a current. If you have a current carrying wire, in fact it has an equal number of positive charges and negative charges, and in fact they're very large amounts of charge. And so although there's zero electrostatic effect, in fact what you're doing is you're adding a really large positive number and a really large negative number and finding that you've got no electric field on a nearby charge. Now if that charge is moving, you say, oh look, because I've got this current, I've got a magnetic field, so it's going to see a force. But of course in that charge's rest frame, there's no force on it, even due to a magnetic field. So what's going on in that frame? Well, if you go into that frame and you look at the charges in the wire, then some of those charges are length contracted because they're moving, and some of those charges are length contracted differently. And what you see is that there's a different charge density between your positive and negative amount. So you actually have relativistic effects explaining what you see in terms of just charges and currents. You have relativistic effects, really dramatic ones, at millimeters per second. So despite the rather radical nature of special relativity's change to our worldview, it is in fact vital to understand the world around us. It's important to see that special relativity came to us from two very, very simple principles: that physical laws are identical in all inertial reference frames, and that there is something that moves at the same speed in all inertial reference frames. So one of the fundamental goals of this course is to help you realize just how sensitive our possible theoretical frameworks are to the principles we use to construct them. So those two simple axioms in special relativity had an enormous number of knock-on consequences to how things can work in our universe. And in the same way, any theory that's supposed to obey special relativity has a lot of constraints. Our first example of that was electromagnetism, when we derived the force law, the four-force law for electromagnetism, almost entirely out of attempting to follow the proper tensor rules. Because if something is Lorentz invariant, in other words, if it obeys special relativity, then we expect it to be able to be written in terms of tensors. And because of the rules of tensors, how we can construct objects, that really restricts the kinds of theories we can come up with. We've already met that kind of behavior in dimensional analysis. If you have a few things that you know are physically related, then dimensional analysis usually tells you exactly how they're related, because there aren't very many ways you can arrange dimensional objects to get things with the right dimensions. This is a stronger version of that. Not only do we have to get the dimensions right, we also have to be able to form valid tensorial relationships between things. And that gives us a really strong constraint on any theory we might construct, whether it be classical or quantum. Now in the last lecture we derived Maxwell's equations, and we discovered that instead of having four three-vector equations, we end up with two four-vector equations, or indeed four tensor equations. You'll note that this one here, the first one, has some kind of relationship between the fields and charges and the way they move, and this other one seems to be just properties of the fields themselves, which are always true no matter what the charges are in the universe. Now, in fact, you might think that this is a sign of some kind of redundancy, and indeed that's true. We already met that there was redundancy in the electromagnetic field, so last year you would have discovered that if you write the electromagnetic field in terms of two potentials, then you have a vector potential A and a scalar potential phi. And if you write the electromagnetic fields like this, then you get two of Maxwell's equations for free. Specifically, the div of any curl is 0, so you get this one for free. And you can show that the curl of E is given for free as well. So these two Maxwell's equations are automatically satisfied if you can write the electromagnetic field in this way. And indeed, these two Maxwell's equations are precisely those that were represented by this equation here, this tensor equation with the antisymmetric tensor. Last year, we would have also discovered that you can write the remaining two Maxwell's equations in terms of this scalar and vector potential. And so we might wonder whether these two equations here, in fact, have some kind of form where we could write them in terms of tensors. Okay, so we're going to start talking about Maxwell's equations in terms of potentials. Then we need to have some kind of tensor-like potentials. We need a scalar, or we need a 4-vector, or some high-order tensor. Now what we have in the previous theories, we have a scalar potential, so we could certainly just use that. But we also have this 3-vector potential, and that's obviously going to cause problems because it's not going to be Lorentz invariant. So we need to somehow expand this vector potential up into at least a 4-vector potential. Well, we already have this component here, so we have 4 components there already. So let's try defining a 4 potential in terms of these two. And we're going to have to talk about our electromagnetic field tensor in terms of derivatives of these things. Now we can see that we've got spatial and temporal derivatives defining our electromagnetic fields here. So obviously we'll need some kind of space-time derivative of this potential here in order to get our electromagnetic field tensor. And it has to have 2 indices. And remember, one of the other properties of electromagnetic field tensor is that it's antisymmetric. In other words, if you swap these 2 indices, you have to get a minus sign. And if we define it this way, we'll automatically get that property. Okay, so if we make these 2 definitions, you can go ahead and show that Maxwell's equations look simply like this. All right, have a really serious go at trying to prove that, and we'll go over it slowly in the next video.